Silman, and I'm an ecologist at Wake Forest University. And I've been working in the southwestern part of the Amazon for the last 30 years or so. So I went down there when I was about 23. Thought I was going to be working on birds, and shifted over to looking at questions of tree diversity. And at that point, trying to understand within plot diversity, so why tropical forests were so diverse, and taking a life history approach to understanding trees. So instead of just thinking about them as stems that are tallied within a plot, to look at them in the same ways that we might look at like salamanders or insects or things like that undergo these radical life changes, and see whether that tells us anything about these forests. And I've spread out to start to think about those kinds of questions in terms of deep time. So thinking about paleoecology, thinking about environmental gradients, and I've also been doing a lot of conservation, both on Andean, Amazonian questions, and also most recently thinking about gold mining and resource extraction, and how you marshal the kind of science that we all do and turn that around so that you can take tropical landscapes and put them back together. What I wanted to do today is talk to you guys who are going down there and just introduce you a little bit to the gradient that we have in Madre de Dios, and tell you a little bit, just some kind of uh, you know, text slides to give you an overview of the how that transect that you're going to be visiting came to be, and then tell you a little bit about the results. And I think the most important thing that I can do for you guys today is just give you a sense of place. And if there are still things that you want to know about the geology, other things about the rivers, any specific stuff, definitely ask at the end. But if there's a break point where you just have a burning desire to know something, go ahead and ask. All right, so I'm going to give you at first the origin story of the Andes Biodiversity and Ecosystem Research Group, and then we'll move into some more science slides. So the research goal of this group was to gain a comprehensive understanding of biodiversity and ecofunction in time and space. So to think about the kinds of things that we think about when we want to go and conserve biodiversity. So basic biodiversity distributions, forest measures, and then start to think about ecosystem function, and then the dynamics, and then think about these things with respect to climate change and other kinds of anthropogenic change. And just to set your mind, when we were thinking about these, this was back in the late 90s and going into early 2000s. And we were working on paleoecological questions. And believe it or not, back then, people were more focused on understanding the climate changes that happened going from the last glacial maximum to the present than any kind of climate change thinking about the future. Back at that time, climate change was about 1 degree C. That was the prediction by 2100, and people couldn't really internalize what that meant. And one of the big revelations that kind of got a lot of people interested in it was that when we looked at the pace of change in the past through the paleoecology, and I'll show you slides on this, when we looked forward to the end of the century, it turned out that the climate change was going to be in an order of magnitude faster. So that got us thinking about trying to understand this ecosystem. There were no plots even of inventory, just a couple of them scattered across the whole South American continent in the Andes. So we had this picture of high biodiversity, but very little ability to explain it. So we started by a bunch of researchers who were working in the lowlands, and we turned our sights towards the Andes. And there was a meeting at the National Center for Ecological Analysis and Synthesis that Brian was at, I was at, and some of the other colleagues that you'll see working on the Andes, and a bunch of other people who thought it either wasn't interesting or was too difficult to do. And we kind of left that meeting and turned our eyes to the Andes and tried to bring the level of knowledge that we had about the lowlands up into this continuous forest gradient. So we started off with a starter grant in 2003, and the whole ethic of this has been a bunch of researchers focusing, so getting some starter money from NSF and from the Gordon and Betty Moore Foundation, and then everyone focusing their individual research programs on the same area, so that we had this kind of stacked and overlapping science going on that would build and inform an area. And just as an aside, as you go through your professional careers, it's been really rewarding because we decided early on, one is that we knew that there would inevitably be people working on the same thing without knowing it, stuff like that. And we decided we were just going to solve all the problems by publishing together, by treating it as a family effort, and kind of the ethic. And it's worked so far. We've been going for, pushing 20 years, more than 15 years, and it hasn't flown apart yet. So what are the components? Well, when we look at the system, we have modern vegetation, so thinking about that, modern ecosystems, and then particularly early on, we had a large emphasis on fire, and I'll tell you why in a bit when we get to the science. We had a large paleoecological component, so we were thinking about how systems performed in the past, and then how we could use that information from the past to give us indicators of how things might work in the future. One of the things that we all find as scientists is, we work on these systems for, within your own lifetime, what seems like an incredibly long time. But when we think about the way that systems change and the pace of change on the planet, it turns out we're getting these brief snapshots. So can we use paleoecology to give us these longer term views of how these systems move? And then we've spent a lot of time thinking about how the system will change in the future and how we can use these results to manage the landscape. And one of the things that's been fairly heartening about this is a lot of the results that we've had from this, and then other things that this has spun off in the southwestern Amazon, have moved directly into policy. And that's one of the things, particularly people working in developing countries, but I find this in the temperate zone as well. As a young scientist, never overestimate what the information that people have to make decisions. It's amazing. There's a lot of pockets of society managing large amounts of land and lots of wildlife that are operating essentially in an information vacuum. So it's a great way to work with people and have your work have meaning. So when we just think about the results, a lot of work on carbon dynamics. We have a fairly comprehensive understanding of the carbon cycle. We have good understandings of tree distributions, and then, surprisingly, still basic understandings of climate and plant-climate relationships. There's some fire results that I'll tell you about that became particularly important when we think about the entire way the system responds to climate, particularly up in the area that you guys are going to be working on. There's been a spectacular functional trait effort that Brian played a key role in, the Chambasa project, I'm sure you've heard about. And I have not updated the Latin American students educated slide for a while, but the other thing that this has become is just a huge training ground. So people from the temperate zone, for sure, but just a real engine for training Latin American students. And I would suspect with undergraduate students, we're probably pushing 250 or 300 students who have been through there. Many of them, maybe even most of them, doing their undergraduate theses, things like that, and also training PhD students and master's students. And what we've developed is an extensive scientific infrastructure to support policy, conservation, and education. So here's a tree in the Andes, and with very simple measurements. Some of the stuff that's been done, I think that you'll see about coupling the remote sensing to ground observations really is rocket science, and a lot of it is just going out and wrapping a tape around a tree or using a dendrometer to understand growth and mortality. All right, so what I want to do is take you to the transect. So here's a picture of at about 3,000 meters of a typical day up in the Andes. So we're thinking about South America. Here's a image of the altitude of South America from the space shuttle to microwave image. So white is high, and you can see the Western Amazon and then all of the sediments that have flown out from the Andes forming the drainage of the Amazon. We're going to focus in on the western part of that, where you guys are headed. Now we see a false color composite from Landsat, and I'm going to pop up my pointer. Hopefully it's showing up on yours as well. So this is the Atacama, the driest desert on the planet. You come up over the Andes, you can see these ranges that are higher than Denali. These bright pinks are wet, high elevation grasslands. And then you come very rapidly. So a few tens of kilometers, you go from snow and ice all the way out into the Amazon basin. And what that does is it gives you a very nice natural laboratory for understanding plant distributions along gradients. And because it's the tropics where it's winter every night and summer every day, we don't have any really seasonal variation in temperature. We do have some cold fronts at certain times of the year, coming more in June, July, and August. But other than that, it's very constant, and the main difference is seasonality in precipitation. So now what I want to do is take you down into the lowlands. So you're standing in the Amazon basin. This is a picture taken from the tower at Los Amigos Biological Station, looking back up towards the Cordillera of Vilcabamba. So again, those mountains are, the highest one behind there is about 6,300 meters. So these are big mountains. And it's important just to take this in. Within your field of view is 1 out of every 9 species of birds on the planet. When we think about trees in this landscape, if we were to take all the ones greater than 10 centimeters dBH going up to the Puna, we don't know the real answer, but it'll be somewhere around 3,000 or 4,000 species even within this field of view. So it's a fairly spectacular landscape in terms of biodiversity. It's also the largest tropical wilderness left on the planet. I think one of the things to remember about this is a place where you could go see the world like Lewis and Clark saw it when they crossed the Rockies, or these early explorers. So it makes a very nice laboratory for trying to understand the questions that I talked to you about in the beginning. And one of the things we've been focused on, you guys are focused on grass and high elevation systems. We focused a lot on the forest systems, trying to understand the different components, trying to understand biomass, the pace of these forest turnovers, and then how things are distributed along gradients, and how that might inform us about how these forests will respond as these gradients change. And I just throw this in. This is a result from the lowlands, and it's one that's kind of interesting and controversial, and it'd be fun to extend this up into the Andes. But when we think about the number of trees in the Amazon basin, it's as many as there are stars in the Milky Way. And when you just think about the basic dominance diversity relationships, that tells us that there should be about 16,000 species of trees in the Amazon. We found somewhere around 12 of those, and then there's these 4,000 vanishingly rare ones. So just to drive home the even within the lowland part of the transect in the Amazon, how little known the place is and vast. And the other thing too, not to lose sight of, you guys are going to be working at at the top of the largest freshwater hydroscape on the planet. I think about 70% of the sediment that comes out of the Amazon River, actually a little bit more, originates in the Andes. And it's got more water coming to the ocean between as the next 5 or 7 largest rivers on Earth combined. So when we think about the Andes Amazon system, we should really be thinking about hydroscape in addition to trees and grasses. And one of the things too that's important to remember about the system is that almost all of these rivers flow uninterrupted from sea to the mountains. By the time you're old, and maybe even not that much older, those rivers are slated to all have dams on them. So understanding the transport of materials in the rivers and the great migrations of the fish in the rivers is an important task as well. All right, these landscapes are beautiful and diverse, but they're also functional. They're intact landscapes. This was a picture taken by a student on one of my courses in the Manu River, so just down at the bottom of the transect. If you guys, well, it depends on where you are. If you spit in the water one way, it'll go down the Alto Madre de Dios, and if you go in another direction, it'll flow eventually out into the Manu. So there's a jaguar laying on the beach, and you guys all study functional traits in plants, but it's also important to remember that there are functional traits in animals as well, and the animal ecosystems are intact, and it also gives us an understanding of an ability to understand how important these things are in regulating forests and forest composition. And at the end, I'll wind up the talk talking about some works on biotic gradients across the Andes Amazon gradient. All right, so here's a picture from our camp up in the Puna. This is taken at about 3,800 meters. Out in the center of your scene is a mountain called Apu Konyahuay. So this is a place that you guys will all be visiting. There's a little house just on the backside of the ridge by the pointer that you'll all be staying in, or at least visiting. And these grasslands are interesting to all of us in their diversity and what they do for ecosystems. And then you can see the clouds and the forested ecosystem starting up at around 3,700 meters and descending out into the Amazon basin. And this is the transect. So this is the Cosnipada Valley, and this is a ridge. It's called the Trota Union, and we chose this ridge because it had a trail in it. One of the things that was most surprising about the Andes is that just how inaccessible they were. There were a few roads that went into the region in the 40s, and people moved to cities, and what that did is it let the forest grow up over trails. And so one of the things we did back in the late 90s, around 2000, is open up trails. And you're standing in this point of view up at 3,600 meters, about, maybe, yeah, about 3,600, some between 36 and 3,700 meters, and you're looking way out into the valley. Down here in the bottom of the valley, it's down around 1,200 meters. So it's a very steep gradient. By the time you get out here, you're at 200 meters. So it's a very steep gradient, and arrayed along here are all the plots. And so this has been our focal study system. So we have a bunch of inventory plots, a bunch of individuals that have now been censused, many of them since 2003. And we set it up so that we would have these plots arrayed at 250-meter elevation intervals. And the nice thing about the entire transect is that that it's such short distance between the plots and elevations that we don't expect there to be dispersal limitations. So we expect to be seeing the effects of actually of climate and plant interactions. And there's just a whole bunch of plants out there, and 1,200 species just along this ridge, and just right down into the lowlands. And William Farfan, who I think is going to be going on your trip, has united the data set from the lowlands. I'll show you in a minute. And so the total diversity in the region is pretty interesting. And now we have a nice record of that coming in and out. So our two transects, so this is the Cosnipada Valley that I was just showing you. And then these are our plots arrayed along there. And then we have a parallel transect down the Cayanga Valley with some additional 1 hectare plots. Then we have actually several more now out in the, we have a plot here at Arica, several plots out in the Panteacoya Range, and one plot that's way back up in the middle of nowhere. I don't know that we'll ever get back to there. So these are our Andean plots. Again, the distances that you're looking over there as a crow flies is just 30, 40 kilometers in the scene. And then as we move out into this area, you're looking at an area that's maybe a little bit smaller than the US state of South Carolina. And then these blue dots are forest inventory plots arrayed throughout the landscape. And just there's been a wide variety of studies done on the transect, so basic inventory to isotopic analysis to different components of tree physiology and ecophysiology, bird physiology, soils. So it's a nice place to work. And this has happened from the Puna, where you guys work, all the way out to the lowlands, because you can put the information into into context, and it allows you to draw a lot richer conclusions from your work and to think about the broader implications of your work. So just a few pictures. This is actually William operating up at high elevation, so just below tree line. He's got a species of Weinmannia that he's collected, and there are bugs up there called puma wakachis that you guys may or may not become familiar with, but if you're moving around, you'll never know that they're there if you end up standing in one place at certain times of the year. Though I don't think the time of the year that you're going, you'll find them. And this is a tree called Incadendron esseri, and this is really interesting. So just to I have another slide on how poorly known the transect was, but this is a tree that's a new genus in the family Euphorbiaceae. And so we often think about finding new species, and perhaps they're segregates of other things or something that someone didn't really know, but they've done the genetics on, and we find out that lo and behold, they're two species. This is a big tree that's abundant in middle elevation, so 1,800 to about 2,300 meters. We found it on the transect, and it was clear that it was something unusual, and ended up being a new genus. And then people started to find it in other places. So they found it in central Peru, and they found it even up in Ecuador, so several thousand kilometers away. Always within the same range, always within that same 500 to 600 meter elevation band. and fairly abundant, again, in the landscape tree up to 25, 30 centimeters in diameter and up to 30 plus meters tall. So it's amazing what's hiding out in that landscape and what we still have to come. When we think about the forested landscape, about a third of our trees are still only ID dimorpho species, even though they've been they've been to all the experts. So it's really, really interesting. So lots of different surprises. One of the other things that that was surprising. One were the distributional changes that we would get. Things would be known from one or two collections throughout the entire Andes. And we would have the second collection of known species, and the first one would be in Colombia, things like that, or Bolivia. So you get these vast range expansions. And the other thing is that many of the dominant species were known from one collection. So it's been interesting to put together the ecology, and with work like Brian does and Yadvinder and other people, in a very advanced way. At the same time, we're just trying to figure out what the membership of that community is. So when we think about climate change effects on Andean biodiversity, I wanted just to talk about a few things. And unless someone pops open turns on their mic and yells stop, I may skip over a few data slides because the conclusions are fairly straightforward, and I think that they've been out there long enough where we can just talk it through and make sure that I have time to tell you a little bit about the animals along the gradient at the end. But what I want to do in the science part of this is talk about tree migration and population sizes in the tropical Andes, and talk about climate change past. So thinking about what I told you earlier, how big were the climate changes in the past compared to the present and future, and how do we know that, and how do we set the stage for understanding that. Talk about climate change present, so just talk to you a little bit about the ongoing work of tree migration now, and then think about climate change and land use in the future, and think about what the predicted changes to populations are, and then think about the migration potentials. And then I'm going to end up the talk again talking about switching from the environmental gradients on the transect, and then going back and thinking about the biotic gradients, so the organisms along the transect. And actually, what I'll do now is I think I'll just stop for a second and give people a chance to chime in and ask any questions that they have up to this point.
Thanks, Miles. This has been great so far. Any students have any questions? Miles, I have a quick question.
You bet.
You focus a lot on all the intensive work that's been going on in the forest plots. Do you want to say just a little bit about the work going on in the Puna?
Yeah, and so when I had some nice video. I don't know if I can switch it around to see. Have these guys, have you shown them pictures and things like that of what the Puna looks like and the
Yes,
landscape?
we've had a little bit. Yeah, definitely. And Ema gave a wonderful talk last week.
Okay, great. Well, I think if I were to add to the context of that, there are these vast grasslands, as Em told you, across the Andes, and they have these very steep moisture gradients. And then when we look at even within the the eastern flank of the Andes, those grasslands have these strong orographic effects, and they're super diverse. So we haven't done a ton of work up in the Puna, and that's why I'm excited about this course, is because it's clearly important. It's a major habitat, and when we think about that habitat moving into the future, it's one that we want to conserve because it harbors biodiversity. I think we've found to date something like 200 species of grass up there, and a really interesting mix of dominance. One dominance a C3 grass, the other one's a C4 grass. So it's a landscape that has a lot of stories to it, and it's also one like you saw where the fire dynamic becomes incredibly important. And as you start to remove fire from the landscape, you get woody encroachment up to a certain elevation. And I have a few slides on that, and I'll talk about it. But understanding that dynamic between the grasses, forbs, the woody encroachment is really going to tell us what's going to happen in the future of the forest as they move up to the Andes. So it's really interesting. And one of the things too, I don't know what the first course found, but one of the things that's always fascinated me about the puna is, we're thinking about grass, we're thinking about the other things, maybe the large ground bromeliads that grow up there and other kinds of things. But one of the things that's most fascinating to me is the sphagnum. The sphagnum is up there. It competes with the grass. It has incredibly fast growth rates. And so understanding that dynamic of kind of woody plants, grass, and sphagnum is interesting. And I think it also plays a very interesting role in succession, both promoting it in some cases and arresting it in the other. If we think about just kind of the general results about the succession in the puna, you guys have talked about fire. I don't know if Emma talked about the ecophysiology, but one of the things that's incredibly impressive to do, if you guys can take along an infrared gun, and everything you've been taught about ecophysiology, is kind of given an exclamation point when you get up into the Andes. So when you're out in the sun, it's super intense tropical sun. You're very close to the equator. It's got the highest UV insulation, I think, or one of the highest of any place on the planet. At nighttime, when it's clear, if you point an infrared temperature gun up at the sky, it'll actually hit its minimum. So it's lower than minus 60 degrees C. So the radiation exchange becomes very important. And it turns out that depending on where you are, particularly if you get out of if you get down in the boundary layer in some areas, you can freeze every night, and it's for seedlings per se with no nurse plants, it becomes very difficult. And so any kind of woody encroachment usually relies on successive waves of tolerant taxa that establish under the grass. They come up and they make a little bit of shade, usually a shrub, protect things from the night sky, and then you start to get seedlings moving in. But we really don't understand that dynamic very well still, though Ken Feely and his grad student have done some good work on that. All right, so let me tell you a little bit about time. This is Gaiadendron. It's a wand shrub. It grows on the high Andean ridges, and we know where that distribution is now. And one of the things we want to think about is, where were these plants distributed in the past? And again, what does that tell us about the system? So I want to take you to a place on the Peru-Bolivia border, so just down the Andes a little bit from our study site in Cosnipada. And we since replicated this actually in the area that you'll be studying in. And talk to you a little bit about a lake called Lago Consuelo. So Mark Bush and I and Duño Orrego went up to this lake. I found it on an outlying ridge in the Andes at about 1,300 meters. And the way you study these things is you just pack all of your coring gear up on mules. You walk up to path's end, and then you put all that stuff on your back and take it up to a lake, and you find places like this lake up at 1,350 meters in the Andes. And we went out and extracted a 7-8 meter mud core and ended up with 50,000 years of climate record. And we can go in and then look at each layer of the mud, dissolve away all the rock and organic matter, and you're left with the pollen. And so these diagrams, you start at 0 years and then go back, and then each one of these different lines is a different taxon. So a lot of these you'll recognize from the temperate zone. So we have things like alder, we have things like blueberries, we have some things, I don't know if you have them in European forests, we definitely have clethra and Mersini and things like that, Acalypha here in the eastern US. All right, and what you see then is the width of the line is proportional to the amount of pollen that's represented, proportion of that pollen in the record. So when you go down, you see that there's a lot of taxa over here, and then as you hit about 20,000 years ago, you start to see these things drop out in composition. You start to see expansion of these other taxa, and these are things that are more known from the lowland. So just with your eyes, you can see that there's substantial shifts going on in the community. And when we think about this, we just ordinate this. You take the first ordination axis and plot that on the x-axis, and it's the calendar year on the y. And you can see there's just two major forest types. It's pretty striking. So you start getting back to 50,000 years ago, and the forest kind of meanders a little bit through time, and we now know that these are traceable to different events happening in the oceans in northern hemisphere. And then starting around 20,000 years ago, all of those deviations from time to time happen in one direction. So none of them are larger than anything in the past, but they just kind of happen in a directional manner. And it shifts the ecosystem to its Holocene state, which it arrived at around 10,000 years ago. And with the exception of one big whammy, which turns out to be the mid-Holocene, so just exceptional droughts, I think a really great analog for the future. The community's been in a fairly stable state. And when we think about this, then we can start to put this into historic rates of temperature change. So we can do a temperature reconstruction, and this is different from modern. So you go back and it's about 6 degrees colder, and still you start until past the last glacial maximum. You have deglaciation. It looks like it overshoots a little bit. Since this time, we think that this is now a signal of drought, where there are just massive droughts in the Western Amazon basin. And this is something too that we don't know its effect on the Puna, but Lake Titicaca dropped by 300 feet in its water level, and it was so dry, and the Amazon basin, the forests of the Amazon, contracted by hundreds of kilometers on its southern margin, maybe almost up to 1,000 kilometers on its southern margin during these droughts. So it's very interesting time in the Amazon basin. But one of the things you can see is that even at the during the largest changes, the maximum rates of change per 1,000 years is somewhere around 1 to 3 degrees. And for most of the time, it's changing about 1 degree C per year. And if we think about the predicted future rates, all of the models lead you to about 4 degrees C for that area of the Western Amazon. There's thoughts that as you go higher, you may get larger temperature changes, though how that translates into plant responses will be I don't think is as straightforward as we think, because of when during the day that those changes are predicted to come. Anyway, let's think about 4 degrees C and think about that. So we take that same figure and we put 4 degrees C on. It ends up being a fairly steep transition, and this is the rate of change. And so it would be something like 3 or 4 meters above your screen. So it's more than an order of magnitude faster than any of the historical rates that we are expecting. This is by the end of this century. And so it really led us to focus on, can species remain in equilibrium with climate? And then what are the population changes if they can't? And then following on from that, the current work about what does that then mean for ecosystems? And I think one of the interesting ongoing changes, and again, this applies to Puna as well as it applies to forest, is what we see is that if you want predictive ability about what's happening in an ecosystem, it turns out that the species itself is the best thing to know. And when we look at, say, things like congeneric replacements and stuff like that, if we look at a genus level response, we can see perhaps a very nice relationship between temperature and some measure of ecosystem function, let's say productivity, but it can be many different things. But when you decompose that, it turns out that every species is pretty much constant, or the slopes can even be reversed from what you would expect. And the way that the ecosystem function changes is that you have turnover in species. So understanding how an ecosystem is built from its component species and how those are going to change, I think is one of the great questions, both in the high elevation grasslands and also down through the forests. And when we think about these systems too, I think we all tend to have this picture of a world where everything is vast and empty. But even within the Andes, there have been people in these areas for a long time. So I put in Machu Picchu to illustrate this. Of course, Machu Picchu is younger than Oxford, right? So Oxford was an old institution, older than Harvard by the time that Machu Picchu was built. But there have been people up in these landscapes for tens of thousands of years. So we have some of the earliest habitations in the entire New World are actually in the Andes. So with these temperature changes, what it says is that, so here's a picture of the Puna forest boundary, is that these forests are going to have to move up, and there's already grassland at the top. And so this question becomes acute, because if these trees can't invade these grasslands, then they're pushed up against a hard barrier, their ranges go away, and the species disappear. So understanding these becomes really important. And when we look out across the landscape at high elevation, so here's a picture taken from one of the sites that you'll have up in the Puna. And just to kind of hit a pause here and tell you a little bit more about the research, a lot of the research that we did up in the Puna was kind of in the early 2000s, some of the first research we did in the transect, and we had a very big campaign in 2006, which I think is where a lot of the baseline data that you're using has come from. But when we look at this, in order for forests to remain in equilibrium with climate, by the time you guys are old and gray, these grassland landscapes have to be forested. The other thing that happens, so lower down on the transect, is the forests are controlled by this balance of moisture. Cloud really does give, cloud, unsurprisingly, is important for cloud forest. And the level at which these clouds form is set by both temperature, and when you would expect that if temperatures were to increase, the cloud base would move up, and that would change the light environment. And then a lot of plants, when it isn't raining, get their water from intercepting cloud directly and actually taking it up through their leaves and branches and mats of epiphytes and dirt that grow up in the canopies. So you would expect it to shift up. That's what we found in Central America. Though if you add more moisture to the system, then cloud base can actually shift down. So understanding this change of cloud base becomes a very important component of the ecosystem as well. So if we look at how species are responding to climate change, we can go to our plots and use the same techniques that we used in the paleoecological studies and just say, if we apply them at modern timescales, can we see species moving? So just thinking about the mean elevation change. And this is something that Ken Feely did when he was a postdoc with me here at Wake Forest. And I have to say, I thought it was a fool's errand at the time, because I didn't think that there was any way that we could see these changes in such a short time period. And he proved me wrong. So what we did is we looked out at the gradient and looked at all of our plots there. And what you see is that each one has a different mean annual temperature. And we can use that to give us a gradient of temperatures. And then we can overlay the ongoing temperature change that we've measured in this area of South America and just see look at things in two ways. One is we can go in and get the distributional data on all the trees and ask each tree, say, tree, if you were going to report to us your preferred temperature, what would that be? And we just take that as the mean elevation of its distribution. And then we can go into a plot and get everything that lives in that plot and query it and just say, what is the mean elevation that the community of trees tells us that it's at? And then translate that into temperature, and then see how that changes through successive censuses. And so that's what we call kind of our community index. And then the other thing we can do is just take the weighted average of each population that we have in the plots and see if they're moving up or down. So kind of an individual taxon-based assay of migration. And just to calibrate you to this, so you can see the Puna up at the top. Now you're standing down at the rivers at the base of the transect. You can see the Puna up at the top. And you see landslides, which are very interesting dynamic that I won't talk about, but I'm happy to talk about with you guys if you're interested in here. But just calibrate yourself. So there are species, we're thinking about a range. There'll be a species that will grow on this ridge. It'll grow from here, it'll go down to here, and it'll be throughout this entire scene. And it will go all the way, in many cases, up to Ecuador, some of them Colombia, yet you will never find it up on this ridge. You'll never find it down here. So how are these things moving in response to climate, and how does the pace tell us about their population? So we used the observed climate change. We used, in this case, just a short interval. William Farfan has since gone on and done that for the entire historical record. And then just looked at the migration, in this case by the 38 most abundant genera, and it contains most of the individuals and most of the basal area. And we did the community elevation score as I described, and then looked at the community scores between censuses and also the mean elevation. What we find when we do this is that you have this broad heterogeneity. So there are things that are having a rapid response to climate change. There are things that are having no response or even a negative. They're shifting what would be downslope. And so we get this mean change that's between 2 and 3 meters a year, depending on whether you look at just individuals per se or whether you weight the individuals by the basal area. When we look at things where we have really good sample sizes, so the abundant trees, this gives you some confidence in at least in the result, maybe not the mechanism, but if there were no result, then what you would find if we were just looking at noise is that that number, the migration rate, should be closer to zero, closer to no effect. And what we find is as we sample more, that we get actually even a little bit higher migration rates. But anyway, a couple meters a year. And if you guys remember the lapse rate of the transect, so it's 5.5 degrees C per 1,000 meters. And so the trees are moving up. The average rates of movement are fairly low, and they're pretty heterogeneous. So I don't know that it's even fair to talk about an average rate of movement because it's representative of almost no taxa. The rates of change that we observe aren't in equilibrium with either current or future rates of climate change. So if we look at the past rates of climate change, yeah, the trees can move. And if we look at the paleo ecological record, the trees are doing, what we saw them do in the past. They're moving around at a couple meters a year. The current rate of change is about 5 to 7 meters per year if you're thinking about the isotherm in the future. So future meaning not that long, kind of going to the end of this century, pushing 10 meters per year. And the other thing that's very interesting is we're looking at lots of functional traits and things like that. We've expanded the samples, but there's no simple trait correlation other than common that gives us predictive ability in terms of its response to climate. So I think that that's very interesting, and it's also an area of study, figuring out, giving any predictive ability for that. The other thing too that has come out of this work and then other work that's replicated in other areas is that a lot of the migration signal that we're seeing, we call it migration, but remember we're looking at the change in the mean elevations. And so that can go a bunch of ways. When you think about migration in your mind, you think, oh, well, it's moving up at higher elevations, and then maybe it's kind of retreating from lower elevations. But the other thing that what we see is happening is it's more like making a track team faster by you can either train everybody to run faster, or the quickest way to do it is just cut the slow kids. And that's what's happening, that a lot of this, what we see as movement, is actually driven at mortality at lower elevations. And what we still have yet to determine is whether it's balanced in the recruitment, in the recruiting layers by increased recruitment at higher elevation. And from the evidence that we have is for most species, it's not, that what we're seeing is a mortality signal due to climate change rather than an actual movement signal. So then we can say, well, what do the populations be in 2100, and what effects do land use have? And the thing to remember about the Andes is it's not like a mountain like Hawaii where the area decreases as you go up. You have a lot of area in the Amazon basin. Area is fairly constant along the Andean slope, but then it decreases again at high elevation. So it's more like the Blue Ridge Escarpment in the U.S. And so here's just some scenarios. Here's the change in population size. If things are in perfect equilibrium with climate, so we look at the mean elevation that plants started with, you're down in the lowlands, you're going to be pushed out of some area onto the escarpment, and so you'll lose population. But a lot of things at high elevation, if they can move up, will do just great. But if there's no migration, climate will leave these things behind. The predicted climate change is actually larger than the range of most of the species. And that's conservative. Actually, a lot of species just get driven completely